So the scientific approach to knowledge. Science is empirical. It's based on experiment. We don't just sit around and think about things. That's philosophy. We experiment. We observe what's going on around us, and we do experiments. So what we call the scientific method is a general approach to learning about nature. And this happens by observing and conducting experiments to test our ideas. So key characteristics of the scientific method, and we'll talk about these individually: observation, formulation of hypotheses, experimentation, and then finally the formation of laws and theories. So I found this video to help us make talking about the scientific method a little more interesting. So hopefully this will work. Dorky music and no words. Okay, something is wrong. I get two of them going, I'm pretty sure. I don't know. Or not, who knows? Let's try that again. There we go, that's better. So here we've got a guy sitting, he's reading a book, he's listening to some music, and he starts looking around and he notices there's two plants near him. And he notices that one is significantly larger than the other, and he gets curious about this. So that's an observation. This one plant is taller. So you can measure that and document, well, how much taller? That's a quantitative observation. Write it down as data. Then he comes up with a hypothesis, trying to explain why. Why is the one plant taller than the other? So he comes up with a couple of different ideas. One has to do with reading, one has to do with music, and one has to do with the amount of light. So he's going to test these with experiments to see if any of these ideas are correct. Computers didn't even look like that when I was in college. So this is his control plant. And then he's going to read to this plant. He's going to read to it every day for a month. Let's see what happens. And I'll read to the plant and measure both of the plants. And this is his experiment. Experiments are controlled. He's not going to just do the one plant because he can't tell if that's going to be just natural growth or if it's due to the reading. Second test, music. So I'll play music for one plant, and the other plant has silence. Measure the plants every day, see what happens. Science can be tedious. Third hypothesis has something to do with how much light these plants are getting. So here we've got one plant in front of an open window where plenty of sunlight getting through. Another plant, they start out the same size. This one's in front of a window that has the blinds closed, not getting as much light. Observe these every day for a month. These are the sorts of experiments you see in elementary school science fair projects, right? And then the results. So test 1, no effect from the reading. Test 2, no effect from the music. Test 3, the sunshine. That had an effect. So the first 2 hypotheses have been disproved. And the third hypothesis has been confirmed. So kind of a fun video. The fact that there's virtually no language in there means that anyone, no matter what language they speak, can understand that. So, any questions right off the bat about the video? Here's my friend the train. Singing me the song of its people. So let's talk about the different steps of the scientific method. Observations. Observations in science are also called data. Sounds fancier than an observation. They're descriptions about the characteristics of behavior of nature. They can be qualitative, meaning you can observe the color of something, or they can be quantitative, like how tall was the plant. That's something you can measure and write down a number. So here we have a historical reference. Antoine Lavoisier lived back in the 1700s. We will see some of these historical figures show up in lecture. They're in the textbook. I think it's important to hear some of their stories, kind of interesting. I am not going to test you on the history of chemistry. I'm not going to ask you what date Antoine Lavoisier died, because I don't remember, and I don't think that's all that critical. So don't stress about any of this history business. So Antoine Lavoisier did some experiments on burning things. I don't know about any of you, but I kind of like to burn stuff, right? Most chemists, I think, are at least secret pyromaniacs. You know, it's fun to light stuff on fire and just kind of see what happens, right? So this guy lit stuff on fire, but he did it with kind of a twist. He burned stuff in closed containers. Normally we burn stuff in an open atmosphere. You go to the mountains and you have a campfire and you stick a log on the fire, right? Big heavy log, and you dump it on there. You burn the log, and later, do the ashes that remain weigh as much as the log did? No. They're very lightweight. You can blow them and they'll fly away in the air, right? So something is happening to the log when it gets burned. Well, Lavoisier burned things in closed containers. And so he was looking at not only the substance that burned, but anything that was emitted from that when it burned. And he found that if he weighed the container before burning the object and after, that the container and its contents weighed the same amount. That is different than what you observe when you burn something in an open atmosphere. So he came up with a hypothesis about this, because we make the observation and then scientists are curious and we want to figure out, well, why is it like that? Just, this is how it is, isn't good enough. So a hypothesis is a tentative interpretation or explanation of the observations. It's kind of a guess, but it's a little more than that. You've thought about what you've observed and you're trying to figure out why. Okay, I think this is what's happening. So Lavoisier explained his observations by hypothesizing that when a substance burns, it combines with a component of air. We know that to be true now. When wood burns, it combines with oxygen from the air, and it gives off two gaseous products, carbon dioxide and water. And in an open situation, the carbon dioxide in the water are going to float away, and that's where most of the mass from the wood went, and you're just left with some ashes. It is important in a good hypothesis that you can test it. If your hypothesis involves, aliens coming down and doing stuff when no one's watching, that's a little hard to test, and so that's not a good hypothesis. So we say a good hypothesis is falsifiable. It's testable. We test hypotheses using experiments. The more control you have over the conditions of the experiment, the more likely it is to be successful. So in our little video, the control there was he used 2 plants for each of the tests. One plant was just sitting there normal, and the other plant he did something to. If we only have one plant and we're testing it and we play music for it and we find that it grows 1/2 inch over the course of a month, we can't tell if it would have done that without the music anyway, right? So experiments need to be controlled. The result of the experiment might support the hypothesis or prove it wrong. So in the video, there were 3 hypotheses, 2 were disproved, and 1 was confirmed. When a hypothesis is disproved, sometimes we chuck it out the window, realize now that was just totally wrong. Other times we realize that we just need to modify it. We just need to tweak it a little bit, and then we take that new tweaked hypothesis and we test it again. So from observations come scientific laws. So a scientific law comes from observations that have been repeated and repeated and repeated. And laws allow us to predict what's going to happen in the future. Probably the scientific law you are most familiar with is called the law of gravity. So the law of gravity allows us to predict what's going to happen. If I take this Sharpie marker and I hold it out at shoulder height and drop it, what's going to happen?
Prediction is that it's going to hit the ground.
It's going to fall to the floor, right? Sure enough, you're right. It does that every time. Because it's the law of gravity, it's true. Does the law of gravity, that objects fall towards the center of the earth, explain why? Nope, not at all. It just says what happens. Scientists are still arguing about what exactly gravity is. Still don't have a complete theory on that one. So from Lavoisier's experiments came the law of conservation of mass. In a chemical reaction, matter is neither created nor destroyed. And we'll talk more about that later. Scientific laws are also subject to experiments, and those experiments can prove them correct, confirm them, or prove them to be wrong. Young children, in particular, like to test the law of gravity, right? Just over and over. That's the baby in the high chair who keeps throwing the spoon out. Testing the law of gravity. That's what they're doing. It's science. You can't get frustrated with them. So scientific laws are different from federal or state laws. There's a speed limit law, Highway 99 out here south of town, 70 miles an hour. That's the speed limit. Can you choose to go faster than that and break the law? Yeah, you can. You cannot choose to break a scientific law. You can't wake up and say, well, I am not going to obey the law of gravity today, right? I'm just going to walk off the top of this 3-story building and I'm going to be fine. No, you're not, right? It just always works. So scientific laws describe how nature behaves. When we have hypotheses that have been tested and confirmed, these can form the basis for a scientific theory. A theory is explaining why nature does what it does. Scientific law says this is what happens. The theory explains why that happens. So the law of conservation of mass was later explained by John Dalton's atomic theory, and this happened in the 1800s, the next century. and we'll talk more about this as well, but the atomic theory proposed that matter is composed of small indestructible particles called atoms, and since those particles merely rearrange in a chemical change, the total amount of mass is the same. So we can go back to the Lego bricks, and you can imagine taking a small Lego set, and you could weigh all the blocks, and then you put them together, and you take them apart, and you make something else, and you weigh the blocks. Has the mass of the blocks changed? No, because the individual blocks didn't change. They are all still there, you just put them together in a different way. And that's what chemical changes are. It's the atoms, the Lego blocks of nature being combined in a different way. So theories also are tested with experiments. Kind of a disturbing idea is that we cannot prove things to be correct. That's a little disturbing. You can't prove something to be correct. You can prove something to be incorrect, but when we test something and our experiments support the hypothesis or the theory, the best we can say is there's no evidence to contradict this idea. That's as close to fact, as close to truth as we get in science. So theories give us explanations, and they can also be used to predict future observations. So this kind of gives us an overview of the scientific method. Scientific method is not a list of instructions, do this, 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 and this, and ta-da, you'll have a scientific paper you can publish. It's not that simple. It's much, much messier than that, which also makes it more exciting and more fun. So what happens here, you can actually start in several different places. I'll just start over here with an observation, like the guy looking at the plants and observing that one's taller than the other. And from the observation, he comes up with a hypothesis. The hypothesis then needs to be tested. It's tested with an experiment. It can be confirmed, like the one about the sunlight was confirmed, or it can be disproved, and you either discard the hypothesis or revise it. And oftentimes you will go around in this circle many, many times. You can spend your whole scientific career in this loop. Sometimes it's tedious, sometimes it's really, really exciting. From observations, we also get laws, like the law of gravity. An object will fall towards the center of the earth. It's just true. And you can test that all you want. It will always be confirmed. So an observation like that, a law, is also tested with experiment. From well-tested hypotheses come theories, explanations for how matter behaves. Those are also subject to testing by experiment. Any questions about the scientific method? So in the textbook, let me back up a little bit. In an ideal world, you would read the chapter before you come to class and puzzle through all the examples and stuff and try to figure it out. And you'd come to class and I'd lecture on it and you'd go, oh, and then, but I still have this question. And then you go home and you read it again. And then hopefully things are really starting to click. That often doesn't happen, so I make some concessions for that. In the textbook, there are conceptual connections and there are examples and then additional for practice examples. And so I choose to do some of those from the textbook in class because I know that a bunch of you aren't going to read it. So I'm forcing you to see it at least. So this is one of those conceptual connections. These typically do not have mathematical calculations in them, they're more thinking. So which statement best explains the difference between a law and a theory? Choice A, a law is truth, a theory is mere speculation. Choice B, a law summarizes a series of related observations, a theory gives the underlying reasons for them. Or C, a theory describes what nature does, a law describes why nature does it. So just think to yourself, which one do you think is the answer? Anybody want to volunteer? B. The answer is B. C is very tempting, but it's exactly backwards. If we change C and says a theory describes why nature does something and a law describes what it does, then C would be correct. A is just plain wrong. Any questions?